abnormal.
You know, yeah.
Everything else.
There are a bunch of other kinds of distributions. We'll learn about several of those. So what that first blank right there, the top blank there, is that question your quote unquote work from now to next week is find out what are some other kinds of distributions. And I don't mean distributions of food stamps and that kind of stuff, but what other kinds of distributions are there? Sample of population data. Let me give you an example. And this, you say, well, geez, you know, we're moving to a different, whole different topic when we say probability. But probabilities, we do a whole bunch of things, we can figure out what the distribution of those whole bunch of things are. Like if you flip a coin, okay? The sample would be how many times you flip that coin and what kind of answers you got. Now, I know you're graduate students, so you could come up with 3 or 4 different results. But let's just assume that we're normal kind of people. That's hard for us to assume, I know. But what are the outcomes from flipping a coin? Heads or tails?
Or error.
Huh?
You could lose the coin.
You could lose the coin, or I just knew someone was going to say, well, it could land on the edge. No. That's the kids do that, you know, they do bottle flipping and all that kind of stuff. Get it to land on it. Yeah. But essentially, flipping a coin there are 2 outcomes. How likely is a heads? 50%. It's about 1/2. How likely is tails? Same amount. So,
I did some research on this online. Yeah, like a 50.5% chance of heads.
Depends on the coin.
The head, there's less relief on that one, so like on the tail side, so it's slightly heavier.
It depends on the coin.
Quarters.
oh, okay.
And if you flip it by hand like that, it has a slightly increased chance of landing on whatever side
It starts
on.
You know.
We,
So-
my roommate and I had this
He's
whole
not
thing.
the
I
only
wanted
one.
goldfish crackers, so we figured it out. It's not a big deal.
But that's what was at stake, was goldfish.
It's a
crackers.
half an hour of my work, but I got them.
Okay.
We didn't have any dice around.
So let's assume that it's 50-50. Okay?
Yes, let's.
Yeah, we can have, are there other, you know, there are all kinds of other possibility, all kinds of other situations where the distribution is somewhat similar. Can you think of any other kinds of things, you know, close to that we might be dealing with, or
Male, female.
gender, male, female? That's pretty close to a 50-50. If you, in actuality, it's not 50-50 though, is it? What is the result, percentage-wise? We're going to do like the flipping the coin.
There are more women.
There are more women, but is that true at birth?
No.
It's not true at birth.
Mortality rates
In
higher.
fact, at birth there are more males. And we're not talking about China, where they terminate pregnancies to ensure that they get a male heir. We're talking about in general in nature. There's all kind of research to support why it is that there are more males born than females. And it has to do with the weight of the chromosomes. Which chromosome weighs more, the X chromosome or the Y chromosome? The X chromosome weighs more. The sperm cell is which size or which one can swim faster?
Male.
The male can, because it's lighter. Doesn't have any more energy or whatever. And so that's the theory about why there are more males born than females. That's one theory at least. If you ask Dr. Gill, she can probably tell you way further than that with her background in animal science. Boy, I get her to talking about some stuff, and she can go way out there. You know, I think it's with chickens, it's just the opposite. And it's again tied to the
Wait, the chromosome?
chromosome.
Really?
Uh-huh.
Because we always order 75 for our show, and we always end up with way more pullets than cockerels.
That's what I say.
Oh, so there's more females?
Yeah.
Okay, never mind.
Yeah, okay,
Opposite.
that would
Proven,
support that.
Proven,
Yeah.
report that
Evidence.
is true.
One bit of evidence to do that.
True news.
So, a binomial distribution may be 50-50. If you graft it, if you graft the distribution, the actual distribution, what, a quarter, what would that graph look like? Have heads and tails, and then you flipped it 400 times. Over here you have frequency, and here down at the bottom you have heads or tails. What would it look like?
2 bars, yeah.
It'd be 2 bars
Or pie.
that are pretty close to the same at the top, aren't they? That doesn't look at all like a normal distribution. Okay? It's a binomial distribution. And a binomial distribution, that's one kind of distribution. What I want you to look up, just internet, Google it stuff, is what are some other kinds of distributions? Economics. Are there different kinds of distributions than a normal distribution? Darn right there are. You know, all kinds of silly looking S-curve kinds of things.
Are you referring to like demand curves and supply?
The supply and demand, you know, or there's distributions for each of those kinds of things. So look up some examples of distributions. We're going to look at distributions a little bit, and we're going to look at probability a little bit. So distributions and probability have this, in a sense, in common to share, or why it matters. When we look at probabilities, those probabilities are distributed based on the number of coin tosses, for example. What is, if we did a series of 10 coin tosses 100 different times, okay? We had 100 different people flip 10 coins and record their results. What kind of results would we get?
You're going to have 100 sets of.
We'd have 100 sets of 10 coin tosses. 10 coin tosses. Did I say coin tosses? What kind of results would we get? Would we get 100 5s and 5s?
No.
No.
But they would even out to it.
They might even out to it. Okay. If we did 100,000 of them, they'd come even closer to evening out, assuming that they were both weighted the same. Okay. What would it cost tossing 10 coins? What's the most likely outcome?
5 and 5.
5 and 5. What's the next most likely outcome?
4 and 4.
4 and 6 or 6 and 4? They're equally likely, aren't they? What's less likely than that?
37.
3773. What's less likely than that? 28, 82, and then 19, 91, and finally 010 or 10-0. What is the likelihood, what is the probability that if we toss 10 coins, we would have either 10 heads, well, then we'd have 10 heads. How would you figure that probability?
0.5 times, 0.5 to the 10th.
Okay, it's 0.5 to the 10th power, isn't it? 0.5 times 0.5 times 0.5 times 0.5, et cetera, et cetera. We can figure that out. Okay? That then gives us a distribution of this binomial activity done with 10 coins. All right? Or 10 times. Let's do it 20 times. What's the most likely outcome?
10, 10.
10-10.
Yeah, 11, 11, 9, 12, 8.
On down to
20,
0,
20.
1.
0 and 20, or 20 and 0. Is the probability of 0 and 20 with 20 tosses the same as the probability of 0 and 10 with 10 tosses?
No.
No, it's much less likely. So all of a sudden, guess what this would begin to look like?
It's another 10 times less likely, right? What does it?
What would it look like? What do you think it would look like? If you did 1,000 tosses of 100 coins, what would the average result be?
You're going to have smaller and smaller.
No, what would the average result be?
500.
It'd be 50-50, wouldn't it?
Right.
And what would so that would be the mean outcome. What would be the mode outcome?
Would it be bimodal?
What would likely be the mode outcome?
If it's bimodal.
Yes, there's a mode. Huh?
Whichever one turns
I'm
out the
just
most.
50-50.
So would it be bimodal?
No.
It would just be
500?
50-50?
It's 50-50 would be the most likely outcome. That's to be the mode.
So 50.
What would be the mean? What would be the median?
50.
Well, some gun now. What would be the likelihood? What would it look like? Would it look like a normal distribution?
No, because it's bimodal.
It would be bimodal. What would be the most likely outcome?
50.
50-50. That's the outcomes are just 50-50, 49-51, etc. It's just one outcome. Why would it be bimodal? What would be the second mode? If 50-50 is the mode, what's the second mode?
No.
There are two of them, is it?
Tails, head, I don't know.
Tails head rather than heads tails?
Yeah.
Yeah. So what would it look like? Would it look like, is it pretty likely that there would be 49-51? Yeah, it's pretty likely that, it's most likely there'd be 50-50. But there'd be a whole bunch of 49-51s.
Is this a trick question? And
No, it's not a trick question at all. It's just logic and
Here's the problem.
probability.
But if you were to plot all of them, they would represent a relatively normal distribution, and you would have.
Okay, we ought to think about that and see if in fact that's true. We could do that with so-called Monte Carlo methods. We did a bunch of those and plotted those and see if it would become, because, what's the likelihood that it would be, if you tossed it 100 times, that it would be 0 and 100?
Very rare, very seldom.
Be very, very rare. But what is that? Would it ever touch?
Asymptotal.
Asymptotal.
So it would be
It
in.
never
the
would.
calculus or-
It never does, yeah, it never does touch the line, does it?
No.
Okay?
um,
Is it a normal distribution or something else? We ought to think about that, look at that sort of thing. Well, let's take something else. Because, they're gonna have Monday Night Football and, they'll toss a coin and they ought to call heads. Except they don't use a quarter, use some other kind of NFL coin, or I don't know what they use, but I don't know if that works. I don't know why, Kyle, but I always called heads. If I had the chance to call it, that's what I called it every time. Just seemed,
Can you apply standard deviation to this concept?
sure, because the numbers are 50%, 49%, 48%, 47%. What's the standard deviation where 68% of these 1,000 times that we tossed 100 coins, what are 68% of them going to look like? If it's a normal distribution, we could figure that out, and that would give us the standard deviation. Well, the question is it a normal distribution? Now, let's think of something else that's probabilistic.
Is one result going to be considered 10 tosses? Is all one result, or is one result each coin toss?
No, it's the 10 tosses.
Okay,
Yeah,
that makes more sense then.
yeah, oh yeah, no, not
It
just.
is per, Michael, then you have two bar, you talked about the bar graph.
Oh no, that's with just one toss. But if we're going to have a distribution of tosses, we have to.
Right.
Okay.
So
Otherwise, we can't have a distribution with just one.
So each series would be one event.
Yes.
Each series of 10 tosses would be
Each
one event.
set.
Okay. Okay.
Okay.
What would that be called?
Just like this test, it's not what you made on one question, it's what you made on all of them. Be the same thing, same kind of deal. Let's take something else. Any of you do the lottery?
No.
You ever done the lottery? No,
Yeah,
lottery.
We understand personal finance.
Huh?
We understand finance when we do the lottery.
Yeah, exactly. You know?
No.
They're fun gifts, I suppose, but that's about it.
Yeah, I've got them before as gifts, never won anything from them. How does the Texas lottery, the big one, how does it work? And they may have changed it.
You throw your money in a pit, and at the end, somebody gets a piece of it.
Yeah.
And the rest goes to education.
What is it?
better.
And the rest
What
goes
is it
to
worth?
Sam.
How does it work?
Well, you throw your money away first.
I know.
None of you know?
It's so little you can't win.
No, not how, well, not what is the likelihood, but how does it work? The big lottery in Texas.
People buy
They roll the
chances at
balls and then they come down the thing
Uh-huh.
and then they set it on the thing and then they're like, this number is 12, and then it lowers the so then you have like a certain percent that you might get that number, and then the number gets smaller because they leave it out of the cage. So then it's out of like 59 balls or whatever instead of like 60. So then the next one comes out. So by the time you get to the fifth number, your percentage of the fact that you
They're
might get
also
that
more
number is
frequent
higher.
though.
So here's what I want us to do. Let's assume there were 50 balls and we're going to get 6 numbers. 50 balls and 6 numbers. What I want you to do is figure out the probability of getting all 6 numbers.
Oh, so you don't have to get them in order.
Well,
You know you do not have to get them in order. You do not have to get them in order. Again, if you've ever played it or ever seen it played or something, did you get the 6 numbers? Did you choose the right 6 numbers?
They have a frequency thing on the Texas Lotto.
Oh, of what numbers?
Uh-huh.
Well, yeah, that's because they haven't done it but 1,000 times, or, you know.
And they do
it's-
it,
won't
and it's
be-
different for every like 6 months.
Yeah, it's gonna be a little different for every number, until they choose another one.
And that's
then-
why I wanted to buy one.
I actually had, I'll just tell you, I've gotta tell you this story. I had, I don't play it, but I told this statistician friend of mine, well, if I did, I'd just choose the numbers 1, 2, 3, 4, 5, 6. And buy that same number every time, because then I wouldn't have to look at my ticket when they pulled the numbers. I would just, I would remember what my numbers were. And that's the easiest number, set of numbers to remember is 1, 2, 3, 4, 5, 6. You know what he told me? He looked me right straight in the eye and he said, well, those 6 numbers aren't likely to be picked. And I said, no, duh. What 6 numbers are most likely to be picked? There isn't any 6 numbers that is most likely to be picked. 1 through 6 is just as likely to be picked as any other set of 6 numbers. The question is, how many different combinations of 6 numbers using 1 to 50 is there?
Isn't there like some kind of way to figure this out with quick math?
No, it's not with quick math. There is a way to figure that out, though.
It's
6 times
72
50.
out of let's see, is that a billion or a trillion?
No, I think you're wrong. It's not.
I did my darndest, I tell you.
Okay, let's do it. Let me start you out.
Do you do 6 places?
One out of
and then
158
50 numbers,
billion.
you would do.
Place 1 has 60 opportunities.
1 out of 50.
No, whoa, there's where you start off all wrong.
No, you do
6
like
out of
6,
50.
would you do 6 spaces, and then it's for 50 numbers, right?
Uh-huh,
And then you keep the ball, you don't put it back.
that's correct.
So it'd be 50 times 49 times 48 times.
Isn't it like 500,000?
It'd be 6/50ths because the order doesn't matter.
50.
What is the, let me,
50 times 1.
no, it's not 1 over until you get to the very end. Let me give you this hint, okay? Let me give you this hint. What is the likelihood if you choose your 6 balls that you'll get one number correct?
6/50ths.
6/50ths. So, in order to get 6 of them right, what do you have to do first?
Get one right.
You have to get 1 right. What's the likelihood you'll get 1 right?
6/50ths.
Oh, it's 6/50ths. Now you got that one right. 6 out of 50 times, you got one of them right.
Dang, that's so.
And then, okay, all right, work with me. This is just logic.
Well, it's not very good logic.
You have
I got
6 out of 50 chances of getting one right. Now, let's assume you got that one right. Now, what's the chance that you would get a second one right?
5 out of 49.
Now you're
And you
getting
multiply
it.
all those
That's
together.
Now you got it. Let me prove to you that's right.
How did you get
Let me prove to you that's right.
Long hand.
No, it's just think about it.
Proportions.
Gotcha.
You're, some of you are childbearing age. Okay?
Or past.
I didn't say that. I said some of you are childbearing age. And so let's work with me.
We can't bear children at all. How do we fall into that?
Your outliers go away.
So
Technically you are.
what's the likelihood? Just assuming. What's the likelihood that you will have your first child will be male?
50.
Well, oh, whoa.
1 out of 50?
50.
How many kids you having?
Depending on the place.
I don't know. What's their born trend?
1 out of 2, right?
Yes.
1 out of 2.
Yes.
Well,
Okay.
that's
Now, what's what's the probability that you will have 2 boys?
1/25. Or one over 1,
This whole class is deluded.
0.25. 0.25.
How'd you figure that?
0.5 times 0.5.
That's right, 0.5 times 0.5.
I got the answer for the lot of
I
them.
don't mean,
He
we're
did
studying
figure it
the
out.
probability,
Huh?
buddy.
Y'all call me
I
up
told you to go write it
Lilla.
on the board.
I'm gonna go write this on the board.
No, you-
I got the answer.
Well, it's very easy to get the answer with the calculator, so.
What?
No,
I'm not gonna multiply those big
You wrote
numbers.
it out.
I wrote it out too and wrote.
But you started out with, you said it was 1 over 168 million, it's not
No,
nearly
that's
that
the
big.
answer.
Huh?
That's the answer.
No, that's not the answer.
That's the answer I got.
Well, it's not right. I will,
Well, I'm gonna listen. I'm gonna shut up. I'm gonna find out what you.
No, write it on the board for the, we're trying to figure out the answer for the 6 and the 6
Yeah.
numbers and the.
Well, now I'm not confident
We've
anymore.
no, you just do the math again. You've got the period in the wrong place is what I tell you, okay?
Oh, so you,
So you were essentially made.
The decimal, okay? And if you get the decimal right, you'll have it correct. Okay, so that's a probability kind of statement. Now, here is what we're gonna work on a whole bunch of things, a whole bunch of times. We're gonna work on not so much descriptive statistics, because descriptive statistics are really things like with just a sample or a population, they're just the mean, the standard deviation, the mode, the median, the interquartile range. All of that stuff is real simple. What we're really worried about in most statistical kinds of sense is estimating the population parameter from a sample statistic. Okay? Now, what is the probability that we take a sample of some population and the mean that we get for that sample is exactly the population parameter mean? In other words, if somehow or other you knew that the mean weight of males at Texas A&M University is 183.786 pounds, and you took a sample of 200 of males, what's the probability you think that you would get 186.738 pounds as the mean in the sample?
The bigger the sample is, the more likely it would be.
Huh?
The bigger the sample is, the more likely it would be fully representative.
It is more likely. What is the probability that you would get exactly 183.687, whatever I said? Or 0.6874382. What's the probability?
Slim?
Yeah, there are two probabilities, slim and none.
I can't remember that.
Yeah, slim and none. You won't get the exact population parameter unless you do what? You do a census, then you get the population parameter. You just describe it. But we typically take a sample. Kyle says the bigger sample we get, the more likely it is to be closer to the population parameter. More likely we are to get it, but we're still not likely to get it precisely, exactly on it. So what we're going to do is estimate the parameter, but just like at the county fair, just like the weight guesser. How does the weight guesser guess your weight?
Averages. He probably looks at your height, kind of estimates what your build would be, and knows about what that would be.
Okay, and then how does he? What does he bet you on?
The average, what he compares it to, like the average he compares it to.
He will never do that.
Oh.
You've obviously not done that at the fair.
Wait, I never did, I showed lambs for 10 years, and at any of our fairs, we never had to guess weights of anything.
No, I'm talking
Talking
about
about
the
the people.
barkers out there in the
It's in the
midway.
carnival, yeah.
Yeah, the
The
carnival.
carnival.
Right,
The
up
party.
folks.
How do they guess your weight?
Yeah.
They say, you know, I'll bet, did they say I'll bet that I can guess your,
I mean, it's
your
when
point
they
weight?
county fair,
No.
that's
No,
what-
they say, they give a range. I'll bet that I can get, because I played this game.
That's right. They say they're gonna get, they can guess your weight within a range. Within a range. They will never do it a point, never. They're not gonna give you a point estimate and bet you a stuffed animal. They're gonna put a range and say, you know, I'll bet you that you're in
Within
between this
5
range.
mi-
Within 5,
miles.
plus or minus 5 pounds. What is that plus or minus 5 pounds based on? You're right. They look at you and they know your height and they can guess all that. And so they say, on average, this guy ought to weigh 168 pounds. But they don't just say 168 pounds. They say 163 to 173.
And it increases their chances of being right.
Huh?
So it increases their chances of being
Well,
right.
increases, it gives them a chance of being right. Otherwise, they'll never be right. You can step on the scale and say, oh, no, it doesn't say 183. It says 183.10, 183.11.
Washers.
You know, they just won't do it like that. What is that buffer? What is that buffer called?
Confidence
It's- It's called a confidence interval. It's called a confidence interval. I am confident. How confident do we want to be?
Pretty darn.
If you're the barker in the midway, how confident do you want to be?
95%.
Well, man, if you were 95%, you're not going to bet with him. You don't give him that much range. And when he says, I'll bet you $1, you're not going to let him use 20 pounds. You only let him use 10 pounds. The narrower the range, the less confident he is. Let's say that, he estimates you're kind of one of these guys that ought to weigh 175. So I'm going to guess 175, but it's really between 170 and 180. What kind of word is he, why does he know to use 5 pounds either side? What is that 5 pounds either side? Basically.
You're right, error.
It's an error, but what do we call it up here?
Standard deviation.
We call that a standard deviation. We call that a standard deviation. He's guessing in the middle, he's trying to guess your precise weight, but he knows that he can kind of be 5 pounds on either side, and that is the standard deviation of his ability to guess. He's guessed so many times he can get within 5 pounds on either side. And how many times will he win?
9 out of 10.
No.
10 out of 10.
Think about it. He's one standard deviation on either side.
68%.
He'll win 68% of the time. Well, geez, he only wins 68% of the time. You think at Las Vegas, if they could win 68% of the time, that they would welcome you to their casino? Heck yeah. How often do they win? About 51% of the time. So all they have to do is win 51% of the time. There's enough people there, and all these idiots go there thinking, well, I'm going to be the 49.
Not today, sir.
Yeah.
Not today, sir.
No. Don't. Oh.
Not today, sir.
Not today. That's right. That's right. And then go to the casino. So, what I want you to do is look up distributions. Okay? Distributions. And calculate what the probability of winning the lottery in Texas. With 50 balls, you have to select the proper 6.
You were right, I missed a 0.
I-
Of course.
Okay.
I knew you.
6 in any order.
You gotta be right, or else you wouldn't have come in here so confidently, right?
That's right, I wouldn't have barked at you. Can we do that?
The first number that was so big is 'cause it was 720 over that. That was before I simplified it.
Yeah, you gotta simplify it. Oh, you had the 720 over the 17,
I did all
1.9
those
billion, or whatever it
fractions.
was.
I just multiplied the fractions across
Yeah.
instead of percentages.
Yeah. Anyway. Okay, there we are. I'll have your grades back next week as well.
I look at mine just to see if there's one or two that I don't remember.
Ooh, me too.
Thanks.